red light's on. I don't know if that means
something's
anything.
working. Okay, so just towards me. And I'll just start off by asking you to tell me your name and just give me a sort of outline of your career, as it were.
Okay, name's Dave Fearn. Originally working at Imperial College for a PhD, then to the University College of Wales in Aberystwyth, working on pulse plasma guns. Recruited after that to work at the Royal Aircraft Establishment in those days, later the Royal Aerospace Establishment, and retired from there in 1998. Carried on working part-time for 3 years, now working as a consultant on occasions, as and when somebody wants me, basically.
Okay, sorry.
I was just to say that the whole of that was, pretty well the whole of that was on effectively spacecraft propulsion.
Great. Okay. Talk to me a bit more about the origins of this work and the origins of the idea of using this kind of propulsion system.
Well, it started back in, I think, around 1908, when Goddard and other people suggested that there was a possibility of accelerating particles of matter to very high velocity by using electromagnetic forces, and therefore providing a propulsive effort. And this was investigated by various people throughout the next decades. Nothing was done, of course, because there were no space vehicles. And as the space age approached in the early 1950s, these studies were taken to a much more concentrated level by various people like Ernst Stuhlinger, recruited by the Americans from Germany, and in the UK by Les Shepard, amongst others, who looked at using this sort of technology for propelling interplanetary missions, and they put the groundwork together of what are many mission studies these days. They showed it was feasible, and they showed there could be very large advantages. But nothing really happened until the space age, nothing experimentally happened until the space age began, and NASA Lewis in the United States got interested in furthering this technology, and various people looked at various different technologies which would allow one to produce these high velocity streams of particles or atoms or gases, and produce the propulsive effects that they wanted. The big advantage of this is the high velocity you can get by using electromagnetic or electrostatic forces, because you're not then limited by the energy contained within a chemical propellant. And that allows you, in theory, to go to any velocity you like. Of course, the power supply then dominates. The first work that I'm really aware of was conducted by Harold Kaufman at NASA Lewis, who developed the gridded iron engine, which has been the subject of most of my own work. But other people, more or less in parallel, work with pulse plasma guns. I've done some work in that area too, with things called colloid thrusters, where you accelerate little droplets of liquid, as in an electrostatic paint sprayer. Field emission thrusters, where that process is taken to the extreme, and instead of accelerating drops, you accelerate ions extracted direct from a liquid surface. And one or two other technologies have come along as well, which have been interesting. For example, the Hall effect thruster was developed in Russia. It was originally thought to be an impossible thing to do in the West. The Americans looked at it briefly and decided it wouldn't work. But the Russians did in fact make it work very well. And it has flown probably 100 times in space. It's the most flown electric propulsion system there is. Other things were investigated as well, other variants of the gridded iron thruster, for example, mainly using different discharge techniques to produce the ions which are accelerated by the grid systems, hence the word gridded iron thrusters. We used the Kaufman technique, which is a direct current discharge in a relatively low magnetic field, whereas the American groups diverged from that and started using a very high value magnetic field with permanent magnets. That's called a cusp field type thruster for technical reasons. And the other type of device, which was developed more or less in parallel, was in Germany, a radio frequency ionization thruster called RIT, R-I-T. And this was developed by the University of Gießen under a man called Professor Horst Loeb, and that's also been very successful. Another variant uses much higher frequency electromagnetic fields than the RIT thruster, work on this has been conducted in Italy and more successfully in Japan. And the current Hayabusa mission to an asteroid to retrieve a sample from that asteroid and bring it back to Earth is powered by 4 ion thrusters using that principle. I think that's a rough scan over the field.
Yep. Okay. Do you want to talk to me in more detail about the work that you specifically have been working, and if you want to talk to me about where you've been doing it and possibly some of the people you've been working with?
Okay. Well, I originally started at Imperial College. I had gained an interest in plasma physics in my 3rd year as an undergraduate because we had what was called a high temperature physics course in those days. That was in fact a basic course in plasma physics. I decided to do a PhD working in the plasma physics group. Started off initially working on what's called a combustion driven shock tube, which is in fact a Centurion tank gun, which was pumped up with liquid.
Actually, that's probably.
They're moving tables.
Yeah.
Sorry, shall I carry on?
Yeah. I'm just trying to think where you can pick up from.
Well, I just start again by saying that I originally worked on combustion-driven shock tubes, and the shock tube we used was manufactured from a Centurion tank gun. The breech was filled with oxygen and hydrogen mixture, which was exploded via an axial wire connected to a capacitor bank. And this explosion burst a copper disc which retained that mixture in the breech, and the shock wave ran down the expansion tube. Shock Mach numbers anything up to about Mach 25. We did work on the plasma physics of that device. Unfortunately, the shock tube didn't behave in a totally reproducible way, so I eventually moved on to an electromagnetic shock tube where the shock wave is driven by an electromagnetic discharge. And I spent a year roughly investigating the plasma physics of that device and also using it for magnetohydrodynamic power generation experiments where you put a strong magnetic field across the shock tube, and the ionized gas which accompanies the shock wave causes an induced electric field perpendicular to the magnetic field, and you can draw current out of the plasma by these means, and you can draw very high currents because the impedance of the plasma is very low. Anyway, I got my PhD for that work, and by accident one of my colleagues at the time, a man called Jinx Cooper, was invited to Aberystwyth to give a lecture at the University of College of Wales at Aberystwyth, where somebody called his name's gone out of my head for the moment, was setting up a plasma physics group, and he was looking for recruits. So Jinx came back to Imperial College and said, there's this job going down there, would you like to apply for it? So I did, and got the job. In fact, I think I was the only applicant. And I joined this new research group. Eric Wooding was the head. His name would just escape me for a moment. And Eric was an ex-Oxford man, ex-Oxford graduate, and he had a lectureship there and starting this group with clearly with government money. And this was very active and a very youthful group, and we did some quite good work. My job was to work on a derivative of the electromagnetic shock tube, which is the pulse plasma gun. In this, instead of running your discharge in ambient gas in the device, you pulse a gas valve and let a puff of gas in, and then run your discharge through that puff of gas at the correct time. And this produces very rapid acceleration, and you can get very high instantaneous thrust values and very high velocities. That was the aim. In fact, the electrical efficiency of this device was very high, but what we call the propellant utilization efficiency, that's the amount of propellant you use to actually produce thrust, was very low indeed. So one number was about, 90%, the other number was about 3%, and the total efficiency you get by multiplying the two together. So it was about 2%, which was pretty pathetic. It was clearly not a practical space application device. It was basically a plasma physics experiment, which was very, very interesting. Anyway, after 3.5 years roughly there, Eric got a readership at Royal Holloway College in London, or near London at Egham, and he moved complete with all the apparatus, all the money and all the people. So I either had to be unemployed or go with him. So I went off to Royal Holloway College and did another year's work on this device, published several papers, and then decided I needed to earn some more money because I was married and my wife was expecting a baby, and we really needed some more money. So I, by accident again, got a job at the Royal Aircraft Establishment. And the accident came about because the work at Aberystwyth had been funded by the Royal Signals and Radar Establishment at Malvern. They lost interest in it, and they trawled around the Ministry of Defence looking for someone who might take it on. And Brian Day at the Royal Aircraft Establishment picked it up, and he therefore became the supervisor of this work. When he heard I was looking for a job, he offered me this job at Farnborough, working on the beginnings of the iron thruster program, gridded iron thruster program. And this used the principles brought forth originally by Harold Kaufman, who I mentioned before. Anyway, Brian gave me the job of building the diagnostics for this iron thruster. But before I did actually design and build quite a few diagnostic systems, but before we did much in the way of experimentation with them, I was given a new job of developing the essential ancillary components needed by the iron thruster, which consist of the hollow cathode to produce the electrons, which are used both in the discharge and as a neutralization system, the electrical isolator, which isolates the thruster from ground, because the thruster has to work at a very high potential, and various other bits and pieces, like, for example, a flow meter to measure the very low flow rates of propellant into the thruster. This work went very, very well, but it was done on a very much an academic basis. So I hate to say it, but our main aim in life was to produce a conference and journal papers, which we did in large numbers. And it was quite an exciting time, and not too much involved. We were not too much involved with financial problems or administration. We just got on with the work. Ideal for an enthusiastic physicist or an engineer. We had quite a nice team. Gradually, the iron thruster, though, got more like a space type of device. It was developed through various marks with very successful physics, both in the plasma of the device and in the ion beam. I should mention in passing here that we were very much assisted by the group at Culham Laboratory, who were interested in this area. Various people there who collaborated on this obtained fairly good jobs in other parts of the space industry afterwards. Foremost of these was Alan Wells, in fact, who went from Farnborough to Culham, led the group at Culham, which worked on the iron thruster, and eventually ended up at the University of Leicester in charge of all their space equipment programs. So I think Alan is still there, actually. Following that, sorry, I've lost track. Yes, we used Culham a great deal. They did a lot of the plasma physics work, a lot of the ion beam physics work, and quite a lot of the design work as well, in particular with grid systems. Anyway, we eventually managed to persuade the powers that be that this technology was suitable for a space application, a space mission. And it was eventually allocated to the North-South station keeping role on what was called variously LSAT, HSAT, and eventually Olympus, which at that time was the biggest communication satellite in the world. And the European Space Agency were involved, and we eventually got to the position where a contract was placed on Marconi Space and Defence Systems at Frimley to act as prime contractor to put this propulsion system onto this satellite. Now, this was an experimental propulsion system that had never been flown before, and ESA wanted both redundancy of both numbers and technologies. So they decided to fly two of our thrusters, one pointing north and one pointing south, and two of the equivalent radio frequency ionization thrusters from Germany, called the RIT-10, again one pointing north and one pointing south. So we were going to have four thrusters for the north-south station keeping application. And there was redundancy, as I say, both of numbers and of technologies. This went on fine. the development program went very well, and in particular we had a very, very successful life test program run by the former Research Institute at Stoke Poges in Buckinghamshire. Now sadly doesn't exist. However, this is how I understand this happened. It's not necessarily completely correct because I was not involved, but I understand that the Department of Industry, who were funding this, decided that they would try to squeeze ESA so that they could cut their budget. And what they said to ESA was that you can carry on with this technology, we carry on providing it, but you'll have to pay for its final development, the final phase of its development. Otherwise, we will withdraw and cancel it. And ESA said, no, you carry on paying for it. And in the end, it was cancelled because ESA wouldn't pay, the Department of Industry wouldn't pay, and it was cancelled. And there was a major international row about this because our removal from this satellite meant that the Germans couldn't fly either. So the Germans were not at all pleased. That cancellation stopped the whole of our program. And there's an interesting point here. Department of Industry, having cancelled it, decided that it might be valid to start it again sometime in the future. And so they ordered all the equipment and all the documentation and everything to be stored in one of our laboratories. Being a bit of a squirrel, I took copies of everything and took it all home and put it in my loft. And I got then moved on to looking at solar power satellites. At the time, there was quite an interest around the world in providing energy in a very, very large way at the multi-gigawatt level to terrestrial users from solar power satellites, which were basically huge, great solar arrays in geostationary orbit. And I was involved in a program to examine the feasibility of these. I spent about a year studying it. We came to the conclusion, interestingly, that there was no reason why these things could not work. The only reason why they might never fly is the enormous upfront cost. In other words, they don't work until you've paid every penny required to put them in orbit, assemble them in orbit and get them to function. So having written the final report on that project, I then became head of the remote sensing unit at Farnborough, where I was responsible for a lot of different things, including setting up the British National Remote Sensing Centre, which still exists in a different form. I was responsible for running the UK ground stations at Oakhanger and Lasham, and for what was called the data centre, where data analysis, image data from satellites was processed.
Pick that up again.
Yeah, I was responsible.
Right.
Yeah, I was talking about the remote sensing unit. The last thing I mentioned was that it included the data processing.
Do you want to just go back and repeat what you said there?
Okay, right.
Yeah.
After the study of solar power satellites, I was put in charge of the remote sensing unit at Farnborough, which had many important functions. Remote sensing was becoming a dominant technology at that time in the space field, and we ran the data reception ground stations at Oakhanger and at Lasham. We started the British National Remote Sensing Centre, which still exists in a different form these days. And we had this data processing centre, which included some very sophisticated and complex electronics for that day anyway, that time anyway. This was in around 1978. The Lasham ground station was mainly used for receiving data from meteorological satellites, and the TV meteorological satellite images shown throughout Britain came from that ground station, and some of them still do, of course. The Oakhanger's ground station was most famously used for getting the data within Europe from NASA's CSAT spacecraft, which was the first satellite to use synthetic aperture radar. And that was operational for only 100 days. It failed after 100 days in orbit. But so much data was acquired during those 100 days that the people in Europe who were interested in that were still analysing some of that data 10 years later. So it was a very long drawn out process, at least from the analysis point of view. Anyway, after 3 years or so of running the remote sensing unit, I got sent to London to head a section in MOD headquarters to give advice to government departments on space matters. We basically analysed where we could what other countries were doing in space, and of course that was primarily in those days the Soviet Union. And we advised government departments as to how they should react, and if, for example, the government had to take a position up in the United Nations, we would offer them our advice. Typically, they very often did not accept the advice, but nevertheless we tried. One of the most interesting things about that time was that a Russian RORSAT, that's radar-equipped ocean reconnaissance satellite, which was nuclear powered, went wrong in orbit and was about to re-enter somewhere over the Earth's surface, spraying radioactive material somewhere, which people were extremely worried about. And we were in the position of having to advise the government on what to do about this. And they got really panic-stricken. And on one night, I was phoned up at about midnight at home to ask if they should shut down all flying over the whole of Britain because they were worried about this material contaminating aircraft. I was able to persuade them not to do this because it was a bit of an overkill answer to a serious problem, but not a problem that was life and death. Anyway, this device did in fact re-enter. It missed Europe, it missed the UK, but came in over the Atlantic, and some of the radioactivity landed on the Ascension Islands, but not to a serious extent. An earlier re-entry of the same type of spacecraft over Canada did cause a lot more trouble because it spread radioactivity over large chunks of Canada, and as you might imagine, the Canadians were not very happy about this, and I think the Russians had to pay some compensation. Anyway, after 3.5 years, I think it was, of leading this group in London, I returned to Farnborough. As a job in London, that was not too bad at all. It was very interesting and not a tedious administrative job like many other people had. Anyway, I was pleased to go back to Farnborough, but there was no definite job for me to do, and I picked up a number of odd jobs. For example, I temporarily ran the organisation doing research in solar cells and solar arrays. And then I became the project manager for the RadarSat program. RadarSat is a big radar-equipped remote sensing satellite, which has been absolutely superbly successful. It was initially a joint venture between Canada, the USA and the UK. And I was project manager for the UK part of this. The plan was to use the Olympus spacecraft, which I've mentioned earlier in the connection with electric propulsion, as the platform, and the Canadians were going to build the remote sensing module that would sit on that platform. And the British aerospace people at Bristol, who took over the Olympus design to do this, were absolutely superb. They worked in collaboration with SPA in Canada, and they produced a very, very good design, which I think would have done the job perfectly. But after all the designs were produced and all the plans were made for full-scale development, the UK government, in its infinite wisdom, decided to withdraw from this programme. This is yet another cancellation which had very bad effects into the future. We withdrew from that programme basically because one of our experts, who I will not name but who I know, claimed that the radar was old-fashioned and out of date and he could do much better. Well, the satellite eventually went ahead with the Americans and Canadians doing it between them after a great international row after we withdrew. And it flies today. It is producing superb data. They've built a second satellite, which is equally superb, and we're now having to buy data from these, whereas we could have been part of the program. Anyway, that's another sad story. But in parallel with that, the people at Culham, with whom I used to collaborate on electric propulsion, ion thrusters, decided that they would like to start that program again, and they could see a renewed market for electric thrusters, and they persuaded I think it was then the Department of Trade and Industry to fund a small-scale effort to get this program going again. But we discovered that all the equipment and all the paperwork from the previous program had been destroyed. Despite the instructions that it should be stored for a restart, it had been destroyed at Farnborough. And there were only the only way in which this program could be restarted was because of all the paperwork in my loft at home, which I retrieved and handed out to all the people involved, and the fact that we had loaned a thruster to the University of Bristol so that they could do some work using argon as a propellant, and they hadn't bothered to give it back. So we approached Steve Gabriel, who'd run that experiment at Bristol, and asked if we could have our thruster back. He very kindly agreed. This thruster went to Culham, was tried on the new propellant of xenon, and worked perfectly. And that was the start of the renewed program. This went from strength to strength. The performance with xenon seemed to be better. I say seemed to be for a good reason in a minute, seemed to be better than with the original propellant, which was mercury, and we got support to carry on with the program. Some of the experimental work was moved back to Farnborough, but as before, the plasma physics and the ion beam physics work was done at Culham, or most of it. At Farnborough, we renewed one of the old test facilities to get things moving, but managed to get funding fairly soon afterwards to build a new facility, and the program went well. Then it was discovered that the superb results at Culham had been partly overemphasized by the fact they were using commercial flow controllers with a guaranteed accuracy of 1% that were actually fluctuating all over the place, and sometimes were no more accurate than plus or minus 30%. So a lot of the results had to be repeated. Anyway, after they had been repeated and we managed to sort this mess out, it was still decided that the thruster was pretty good and should go ahead. Development continued. We got to the stage where we could claim it was flight worthy, and we interestingly went for a similar thing to the earlier Olympus program. We were scheduled to fly on the Artemis experimental communication satellite, if you like, a grandson of Olympus, and in exactly the same way, with two of our thrusters pointing north and south, and two of the German thrusters from the same German team pointing north and south again. So it's an exact repeat of what should have happened on Olympus. Only this time it didn't get cancelled, and this time it flew. The prime contractor for this was Matra Marconi down at Portsmouth, and they designed and built the power conditioning system for this thruster and the propellant feed system. They actually built the thrusters themselves as well, because we lost control of the program and it was basically passed to industry. Sadly, the design of the power condition, a design of an aspect of the power conditioner proved to be inadequate. And both of the UK thrusters did not function for any length of time in orbit. The problem was not the power conditioner itself, but the cable between the power conditioner and the rest of the spacecraft. Sorry, I've said that incorrectly. The cable from the power conditioner to the thruster.
Can I just say that sentence again, so it's a complete sentence?
Yes, the problem concerned the cable between the power conditioner, which is quite a big box set back within the satellite, and the thruster itself. This cable was very, very badly designed. And looking at the design now, one wonders how on earth it ever got through the many, many design reviews, critical design reviews and so on. But it did, it got through these review processes and was built and flown, and it caused the failure of both systems. Luckily, the German systems worked fine. I say luckily because the Ariane 5, which launched this spacecraft, partially failed, and the spacecraft was put in a totally inappropriate orbit. The electric thrusters on this spacecraft then allowed it to be, the orbit to be raised over a period of many months, so it eventually attained the correct orbit. If those electric thrusters had not been on board, the mission would have been a total failure. So it was an example of how electric systems can rescue a mission that's in trouble. That spacecraft is still operating. It includes a number of totally innovative technologies which have all proved to be very successful. So it's been a big success story. One of the technologies on it, in fact, is a laser transmission system, which allows transmission of data between geostationary orbit and low Earth orbit remote sensing satellites. So basically what can happen is a low Earth orbit satellite collecting, shall we say, optical imagery from the ground can transmit the data up to Artemis, and then Artemis can transmit the data back to a ground station anywhere within its very large footprint, which circumvents one of the problems with remote sensing satellites. That is that they're so low down that they can only see a small surface of the Earth at a time, and their passage time over a ground station during which they can send the data down is only about 10 minutes. So that is a solution which will go into the future. Following that success, the thruster was allocated to the GOCI mission, the Gravity and Ocean Circulation Explorer mission, which is an ESA mission to measure very, very precisely the Earth's gravitational field, much more precise than has ever been done before. And there is a particular peculiarity about this mission, and that is that the aerodynamic drag on the satellite, because it flies very low, must be cancelled absolutely exactly by the propulsion system. And the only way you can do this is by taking a gridded iron thruster and throttling it in exact response to the air drag. And no other electric thruster, or in fact no other chemical thruster, can do this. So it's a unique application. It's never been done before. It's not been flown yet, but it's scheduled to go at the end of this year. So that will be another application of that particular iron thruster. During the development of that one, which was called T5, T stands just for thruster, we also developed a bigger thruster called the UK-25, which generates up to 300 millinewtons of thrust. I should go back and say that the T5 generates somewhere between about 10 and 30 millinewtons. The UK-25 is 25 centimetres in diameter, as the name signifies, and it produces up to about 300 milligrams. That was designed for the Comet Nucleus Sample Return mission.
Sorry, 300 milligrams.
Milligrams. Sorry, millinewtons.
Yeah.
Thank you.
Sorry. Take that sentence again.
Yes, sorry. The T5 produces a thrust of around 10 to 30 millinewtons, which is a very small amount, but nevertheless adequate for the jobs for which it is intended. The UK-25 goes up to about 300 millinewtons. It was intended originally for the Comet Nucleus Sample Return mission, which was an ESA mission, as the name implies, to go to a comet, pick up a sample and bring it back to the Earth. That mission turned out to be too expensive and was cancelled and was replaced by Rosetta, which of course has not got electric propulsion on it. So there was no mission for this thruster. So it sits in abeyance. It's available if anyone wants it, but it sits in abeyance. In parallel with that, we looked at the market for communication satellites in the future and decided that a thruster with a thrust of the 150 to 200 millinewton range would be more suitable for modern communication satellites, weighing up to about 6 tons. So I personally designed the T6 thruster, which is now accepted for the Alpha Bus, which is the new up to 6 tons communication satellite being developed in Europe. It's unique in having, I think it's unique in having a solar array which can go up to about 25 kilowatts. Very, very big satellite, very, very high power. It needs a very efficient propulsion system, and the T6 is the one that we hope will do that job. Simultaneously, ESA became interested in going to the planet Mercury and decided to do this on the cheap if they could. Not surprisingly, they haven't got endless sums of money. And the way of doing this inexpensively is to fly on a cheap launcher, a Soyuz launcher. But if you fly on a Soyuz launcher, there is no way you can get to Mercury and go in orbit around Mercury with chemical propulsion. You have to use electric propulsion. So at the moment, the BEPI Colombo mission, as it's now called, is going to be powered by T6 iron thrusters. And Kinetic, as the organisation that originally was RAE has become, has a contract to provide these iron thrusters for the BEPI Colombo mission. It's worth just mentioning in that context that RAE, Royal Aerospace Establishment, eventually became the Defence Research Agency when it got combined with other Ministry of Defence establishments. Then as more Ministry of Defence establishments were brought in, it became the Defence Evaluation and Research Agency, DERA, and then it was privatised, and that is now Kinetic, which is a private company. Sadly, that process was accompanied by a change in emphasis. RAE was originally able to conduct blue skies, as it's called, original research with a very, very long time scale. The ion thrusters could not have been developed without that, but that time scale has now been whittled and whittled away, and now if you come up with an idea that doesn't reach fruition in faster than about 5 years, you can forget it. There's no money for it. There is no development money for long-term research, and it's getting worse. It's getting now to the stage where you can only do development work, you cannot do fundamental research work. That's a sad comment on what's happening in universities as well, where the same problem applies. Anyway, to take my own position, I formally retired in 1998, having been head of the UK Ion Propulsion Programme for some years. Neil Wallace took over that programme from me, and he's now running a very effective organisation, but always faced with funding problems. It's a perennial problem that he has to tackle. I worked part-time for 3 years after formal retirement, working on the physics, mainly of hollow cathodes actually, which are part of the ion thruster. Then finally left in 2001 and decided to carry on as a part-time consultant, partly for Kinetic, but I've also done work for various industries, various companies like SNECMA, for example, in France, and for the European Space Agency directly, and a couple of jobs for other organisations like the USAF. That's probably it, I think.
What? Excuse me. What's the deep space ion?
Deep space, yeah. Deep Space 1 actually was the first interplanetary mission using ion thrusters. It was a NASA mission and it was superbly successful. It uses their 30 centimetre thruster, which is a much bigger thruster than we've developed in the UK, but it's downgraded so much that it produces far less thrust than the T6. Its peak thrust is 98 millinewtons. Anyway, it was launched on a trajectory towards an asteroid, and I've forgotten the name of the asteroid. And the ion thruster was run continuously to propel this spacecraft towards the asteroid. But there was a navigation problem, and it missed. It didn't go close enough past. So this demonstrates the flexibility of this type of system. If this had been a ballistic mission, flown with just a high velocity from an original rocket launch from Earth, that would have been the end of the story. It wouldn't have been able to do anything else. But they were able to redirect it to another asteroid, which it got very close to and photographed, and it was very successful. And then they redirected it again to a comet. And they took it very, very close to the nucleus of this comet and took some brilliant photographs. I think the only sensor on this was a camera. It wasn't a truly scientific spacecraft. It was a technology demonstrator spacecraft. They flew it very close to this comet nucleus. Got I think the best pictures ever of a comet nucleus. And they were going to redirect it to another small body, either another comet or an asteroid. But the ground segment cost was getting prohibitive, and so they cancelled it. I think they tried to give it to a university, but no university could afford the ground segment cost, so it was shut down. But the ion thruster in space did about 18,000 hours of operation, which is a record. And the ground test thruster, which was run at JPL for more than 30,000 hours. So both on the ground and in space, it was very, very successful indeed. It's one other point to mention. It was almost totally autonomous. It had a very interesting beacon system on it. This beacon transmitted at, I think, 4 frequencies. And if at one end of the frequency spectrum, a signal basically from that side of things said, I'm in perfect health, I've got no problems at all, don't bother me. And at the other end, the 4th frequency, whether it was up or down, I don't recall, basically said, help, I'm in dead trouble, contact me quick. and using this, they were able to cut down the ground segment cost very, very considerably. But it's led to another mission called Dawn, which is going to be propelled by a slightly upgraded version of the same ion thruster. And Dawn is a truly scientific mission, not a demonstrator. And it's going to the big asteroids, Vesta and Ceres. They're sort of hundreds of kilometres across. They're very big asteroids, and they're going to investigate those two over a period of several years. And there are several other missions coming along. So this technology has really taken off. The other thing to mention, which I think I did right at the very beginning, is that the Hayabusa spacecraft from Japan, from JAXA in Japan, has done absolutely brilliantly as well. That is only, I believe, 530 kilograms at launch, yet it's gone to an asteroid. It's landed on the asteroid. Sadly, they had a problem. So the sample retrieval system that they used to take a sample from the surface of the asteroid has worked, they think, but they're not sure. They can't confirm that it's worked. Anyway, they're going to fly this back to Earth and return this sample, assuming they've successfully got it, back to Earth for laboratory analysis. And this is all being done with a 530 kilogram spacecraft powered by 4 small ion thrusters. So the message really from these latest experiences, and from Bepi Colombo in the future, we hope, is if you want to go somewhere in deep space, and if you want to do it efficiently and effectively and quickly, ion propulsion is the thing to use. But it doesn't mean there aren't other ion propulsion systems as well, which can do very good jobs. Just finally mention, once again, the Hall effect thruster. That was pioneered by the Russians. It's been superbly successful. It's flown on something like 50 or 100 spacecraft. I don't believe it's ever had a failure. It's been picked up by the West. The Americans are building them for communication satellites, as are the French. SNECMA build small ones and quite big ones for communication satellites. And last point is one of their thrusters, the PPS-1350G, powered the Smart 1 mission to the Moon. Smart 1 was launched into a geostationary transfer orbit, and was propelled to the Moon by one of these Hall effect ion thrusters, very successfully.
I'm going to be a real pain. Can you just tell me why ion thrusters are so good? And you can talk about SI numbers and I think we've sort of done that anyway, but I'd like to just get that into a nice, concise sort of...
Okay. Chemical engines of any sort...
Can you just remember to keep looking towards me?
Oh, sorry.
It looks a bit odd if you're looking into the lens.
I keep looking there, yeah. Chemical thrusters are limited always, and must be limited, by the energy available in their chemical reactions. Basically, in any rocket engine, what you're trying to do is send out an exhaust at high velocity. The higher the velocity, the better, because the more effective the device is. This effectiveness is defined by a thing called the specific impulse, which is the thrust divided by the rate of flow of propellant in weight terms. So the higher the thrust, the higher the specific impulse, and the lower the propellant flow rate, the higher the specific impulse. But as I said, you are limited with a chemical system by the energy available in your chemical reaction. If you can accelerate your propellant by some other means using electrical power, you're not faced by that limitation. And there are 2 ways this can be done. One is by using electromagnetic forces, which is what you use in pulsed plasma thrusters, for example, and the other one is by using electrostatic forces. In the electromagnetic version, you have a current through a plasma, and that current interacts with a magnetic field, which provides a force, as in an electric motor, which directs the plasma out of the device at high speed. You can get very high speeds by that means. In the electrostatic version, you turn your propellant into an ionized gas, a plasma, and you extract the ions from that plasma via a grid system, and you accelerate them between those grids by a very high voltage, and that voltage gives you a very high exhaust velocity, and there is no actual limit to the velocity you can achieve. Typical ion thrusters achieve a velocity of around 30 or 40 or 50 kilometers per second. Sounds very fast, but in fact you can go much, much faster than that. That is a specific impulse of up to around 5,000 seconds. sorry, it's a funny unit, but if you define specific impulse in the way I have, and it's the engineering way, the unit is seconds. It sounds peculiar, but it is. Anyway, you can get about 5,000 seconds. For comparison, the best you can do with chemical thrusters without using nasty exotic materials is with liquid oxygen and liquid hydrogen, and there the value is around 450 to 470. That's 450 to 470. So your 5,000 is 10 times up on that. But if you want 50,000, you can have it. The only limitation is the engineering that's involved, which is, by today's standards, fairly trivial, and the power available. And in fact, there are some experiments going on at the moment at the European Space Agency, ESTEC, in Holland, which have achieved specific impulses of 20,000 seconds using xenon. And if they had in fact been using a lighter atom like helium, they would have got 200,000 seconds for the same voltages. So the value is available if you need them. But the point is, you can't just say it's always better to have a higher specific impulse. It depends on the mission and the mission parameters. So for any application, you have to do some emission analysis and decide what the optimum is, and then go for as near that optimum as you can get. But generally, for deep space missions, which require lots of energy, the higher value is necessary. Okay?
Perfect. You did exactly what I wanted, actually. You compared it with, LOX hydrogen motors.
Yeah,
and
that's right.
Go that sort of is there anything else that you think we need to... I mean, are there any little anecdotes or anything like that that you'd like to...
Probably not really relevant.
No.
I mean, you can go on and on about personalities, but there's nothing sort of really funny like Alan losing his rocket in the wood or whatever, or this Hungarian guy. I'm sure there have been things like that, but they're just not. Just don't spring to mind at the moment. No.
I mean, there's no other points that we've sort of missed.
Well, you could go on forever.
Yeah.
I mean, the stuff about, for example, the stuff about my time in London, there were quite a few funny things happened there. I mean, I was on a committee that was discussing nuclear power in space, and this was chaired by a general, a sort of fairly elderly general, and he would routinely start the meeting, say, first item on the agenda, apologies, second item on the agenda, minutes of the last meeting, then he'd go to sleep. And his adjutant, who was a sort of, a major or something, would then automatically take over as chairman. And then, towards the end of the meeting, the general would wake up and say, where have we got to then? and it happened every time.
This is what's great, actually. I mean, obviously the sort of history of things is brought to life by little anecdotes like
That's
that.
right.
It's just amazing.
And the other, I got both horrified and amazed about some of the people in London. For example, we had again on nuclear power, we had a cabinet committee group, cabinet office group rather, who were dealing with the way the way the UK should approach nuclear power in space with regard to United Nations resolutions. And we had these meetings, and we'd had 2 or 3 of these meetings. And this guy, who was part of the decision-making process, said, a bit embarrassingly, could anyone tell me what a nuclear reactor is, please? And he was going to advise the government on what to say to the United Nations on nuclear reactors. On the other side of the house, there's a thing called COCOM, there used to be, which was to do with authorising technology transfer to places like China and so on. And an American company won a satellite project, and this satellite was to be supplied. No, it was going to be launched on a Chinese launch vehicle, and we had this meeting to discuss what should be done about this, and it was quite a technical meeting. and it's chaired by a guy from the Foreign and Commonwealth Office. And this meeting went absolutely swimmingly. This guy chaired it fine. It sounded as if he had been in satellites all his life. Asked all the right questions, made all the right comments. Meeting was superb from the point of view of sorting this problem out. I discovered afterwards that he'd been in the job 2 days. He'd been transferred from somewhere else, and his first job was to chair this meeting. He knew nothing about satellites or anything, and he sounded as if he was a world expert. So he was very, very good. It's guys like that who make a good ambassador, I should think.
I mean, it's the usual old thing. As soon as you turn the camera off, people say, I just like you to...
Yeah, one's career is a mixture of successes and frustrations. It's the thing that keeps you going is the successes you achieve, the technologies you develop, the missions that are successful. You can tick them off on your list as being successes, things you can be proud of. But the frustrations are enormous, predominantly due to funding problems or the lack of funding, but also to some stupid administrative things which you wonder about. You cannot see any point in them, but somebody demands that you undertake them. One just simple example of this, many years ago, we were all asked at Farnborough to provide a list of all our competitors in the whole world. We had to give fully detailed information about all our competitors, and it took me something like 2 weeks of work to do this. And I discovered afterwards that these documents, which had taken all this effort, were just stuck in a filing cabinet and forgotten about. Very, very frustrating.